Swayam Prabha. Digital India. Educated India.
Hello, welcome back to lecture 2 of Aerospace Structural Analysis. In the last lecture, we have given a brief introduction, the motivation of the course, the objective of the course, and also discussed why aerospace structures are distinct and what is the requirement of a dedicated course on learning to design and analyze aerospace structural components. In this lecture, we will be continuing the introduction, give a brief history of how the aerospace structure evolved over time and how the present day aerospace structure came into picture, and we will also introduce the different important component of the aircraft structure. So, let us start with a brief introduction to the background or the history of how aircraft structure developed. In the last lecture, I started talking about the background. So, we started with the person Octave Canute, who is called the father of aerospace structure. So, as I said, he was a bridge engineer with railways, and he had designed several advanced bridges for the railways. So, after his retirement, he invested his time in developing flying machine, lighter than air flying machine, not powered aircraft that we see these days, but he made a major development in the aerospace structure. So, in this lecture, we will discuss how these structures evolved. So, Canute used a truss structure, a wooden truss structure made out of he developed this glider that is seen in this picture. So, in this glider that is seen in this picture, we can see that a truss construction has been used. Each member of the truss, as we know, is a two-force member, and the top and bottom portion of the truss was covered with linen to give aerodynamic surfaces. So, this glider was very lightweight structure because of the truss configuration, but it was a biplane structure, as you can see from the picture. This biplane obviously gives rise to slightly higher drag as compared to the monoplane structure that we see. So, the next worth mentioning after Canute's truss structure was the design developed by the famous Wright brothers. So, as we all know, the key to the success of Wright brother is the use of control surfaces, and there were the first heavier than air powered aircraft which actually flew for 12 seconds in the first demonstration. So, they also had a biplane as developed by the Canute, and on the right hand side you can see this, airframe of the schematic of the airframe that was designed by the Wright brothers. So, you can see a similar wooden truss kind of structure, each member being a two-force member. So, the total weight of the airframe was around 405 pound and the engine weighed around 200 pound. So, though the major contribution of Wright brothers were in development of the control surfaces and the powered and the concept of powered and heavier than air aircraft, they also made a considerable advancement in the aircraft structure. So, they had such good understanding of the basic mechanics and structural mechanics that can be seen from the elementary yet elegant design that they have developed. So, the patent that they filed, a small portion of the patent I have given in this slide. There you can see that they had discussed the aircraft, the structural part of the aircraft. They said that the airframe was made out of spars, bows and ribs and constructed using wood, having both strength and lightness and flexibility. The framework, upon the framework, the cloth which forms the supporting surface of the aeroplane is secured. Okay. They had such good understanding that while they wrapped the fabric or the cloth over the airframe, they made sure that the thread of the fabrics are arranged diagonally to the transverse parts and the longitudinal ribs. Now, this is because the fabric or the thread of the cloth actually are much more stronger than the other direction of the cloth. So, they intentionally put the thread or the fabric at 45° or diagonally so as to resist the shear force. So, the longitudinal ribs and the transverse bars were withstanding the normal forces, whereas the fabric which was given diagonally was utilized to withstand the shear forces. So, you can see with the minimal raw material that they used at that time, they made the use so judiciously that they used the fiber also to withstand the shear force apart from the spurs and the ribs that were used for the normal forces. So, this is an example that I have put primarily to emphasize that how the understanding of basic mechanics, the basic idea of mechanics that the maximum shear will happen at 45° helps us and helped those engineers and designers earlier also to find an effective design which was successful. It was not a rocket science, but a very simple understanding, but clear understanding of the mechanics. So, after Wright brother, the next design that needs to be mentioned is the one designed by Blériot. It was designed in 1909. It was a monoplane structure. Unlike the one developed by Wright brothers and Canute, which were biplane, this one is the first monoplane structure. As you can see that the monoplane, that the wings are actually supported by wires which are connecting this wing to a post at the center just below the fuselage. Okay. So, this design also here there is this bar and there are wires which are supporting the monoplane or wing to the fuselage. So, this monoplane design help in reducing the drag considerably, make it more aerodynamically efficient, and this made a flight across the English Channel at a speed of 60 miles per hour. This was a big feat achieved, and this design became very successful. So, post this design, there was a major change in the design of aircraft structure. So, till Blériot, it was seen that a truss structure was used. a two-force member wooden truss structure was used to make the wing, the fuselage and other component of the aircraft. But Becquerel developed a monocoque design. The word monocoque means single cell. So, the monocoque construction means a single cell construction. The essential feature of this monocoque structure is that instead of using a truss structure, in 1911 a person, an engineer called Louis Becquerel, he tried to glue layers of wood and make a thin hollow cylindrical shell kind of structure. So, each layer of the wood was glued to each other and this monocoque structure was developed. So, this monocoque structure has the advantage of being much more lightweight than the truss structure. So, he in the design that he developed, he made this fuselage out of multiple layers of wood to create a streamlined shape. And the monoplane that was designed by Becquerel using this monocoque structure could fly at a speed of 125 miles per hour, which was a big leap from that developed earlier, which were flying at an average of 50 to 60 miles per hour. So, this monocoque structure hereafter became very popular and people discarded and engineers discarded the truss structure and moved into this monocoque or hollow cell kind of structure. So, Depardieu, which was developed in 1912, is a classical example of another successful monocoque design of plane. Here the fuselage was also made out of 3 layers of tulip wood reinforced with intermediate layer of fabric. Please note that no more any other truss kind of structure was used. So, but there was one disadvantage of this monocoque structure. The primary disadvantage is that it required very highly skilled craftsmanship or workmanship to develop this monocoque structure from wood. And this also became expensive because a larger extent of wood was being used to develop this kind of structure. So, because of these disadvantages of monocoque structure, the disadvantage primarily being the huge cost associated and the very skilled craftsmanship required to develop this structure. And again, as the size of the aircraft started increasing, this monocoque structure had more disadvantages, because you can understand from your intuition that such hollow shell-like cylindrical cell-like structure would become very vulnerable to buckling as the size increases. So, as the aircraft started becoming larger, the monocoque structure was no longer very effective. So, the next development or the next improvement that happened over monocoque structure is the semi-monocoque structure, which is all the aircraft that we see even today are semi-monocoque structure. So, what is semi-monocoque structure? As the name suggests, semi-monocoque structure is a monocoque structure, but it is reinforced intermediately using longitudinal and transverse members. As you can see from this picture, it is a monocoque structure, but we have this reinforcement. this longitudinal reinforcement and this transverse reinforcement. So, transverse reinforcements are sometimes have several names. They are sometimes ribs, formers, bulkhead, and the longitudinal reinforcements are stringers, longerons, spurs. So, this reinforcement actually prevented the buckling of monocoque structure as the aircraft became larger. So, as the aircraft became larger, the size of the monocoque increased and they became very prone to buckling failure. So, to prevent this buckling failure, this monocoque structure was being reinforced longitudinally and transversely, and that gave rise to semi-monocoque structure, which were much more stable to buckling failure, and a semi-monocoque structure is the present day aircraft design that we see. So, semi-monocoque, so we can see, so this is a semi-monocoque structure where we can see all the reinforcement longitudinal and transverse, and this is a monocoque structure where we do not see any reinforcement. So, that is the essential difference between a monocoque and a semi-monocoque structure. So, these days monocoque construction is almost obsolete. You hardly can see any plane with a monocoque structure. What we see is a semi-monocoque design. Now, with the first plane that was successful using a semi-monocoque design was the Junkers F-13 passenger airplane, which made its first flight in 1990. So, this Junker was another development was that it was no longer made out of wood, but it was made out of metals. So, because as I said, the availability of wood was becoming scarcer, and the engineers, the aircraft manufacturing people had to move from wood to metal. So, unavailability of wood was one of the reason. The second reason was that the wood was very prone to decay and structural failure, and the start of use of metal prevented this kind of structural failure that was very much seen with the wooden aircraft structure. So, around 314 F-13 Junker airplanes were produced between 1919 to 1929 and was in service with more than 60 airlines between this time, and finally they were replaced by more advanced versions. So, these are the pictures of semi-monocoque structure. These are the schematic of semi-monocoque structure. This is that of a wing, a semi-monocoque wing. So, as you can see in the semi-monocoque wing, the outer layer is the skin. The fabric that we said for the fabric that we have seen for Canute and Wright brother were later replaced by metallic sheet, and this metallic sheet is what we call the skin. So, beneath the skin, if you look beneath the skin, there are these longitudinal members that you can see. Some of these longitudinal members extended along the entire length of the wing, and some of the longitudinal members were only in certain portion of the wing. And you can see, so these longitudinal members are have several names. Some of them are called spars. Spars are usually the heavier member. I will come into the detail of this later. Some of them are called stringers. So, these are longitudinal members. Apart from the longitudinal members, you can see these transverse members which are seen at intermediate location along the length of the wing. This transverse members are also has different terminology. One common name for them is the ribs. The transverse member that we see in a wing are called ribs. On this figure, we see the semi-monocoque structure of a fuselage. So, we see the semi-monocoque structure of a modern fuselage. So, here also you can see that there is a skin, okay, which forms the outer layer of the fuselage, which gives the aerodynamic surface and reduces the drag. But if you look inside the skin, you will again see that there are longitudinal member running through the length of the fuselage, and then there are transverse members, as you can see. So, these transverse members are in case of fuselage are called bulkheads and former, and the transverse and the longitudinal members are called the stringer and sometimes also longerons. We will talk about this later. So, these two figures give you a fair bit of idea about how the semi-monocoque structure look in modern day aircraft for a wing as well as for a fuselage. So, similar semi-monocoque structure are seen in other component of the aircraft also. If an aircraft have a tail-like structure, the tail also has this kind of semi-monocoque design. So, here we will be talking in detail about the different structural component of a semi-monocoque wing. So, this shows the cross section of a semi-monocoque wing structure, as we can see, cross section of a So, as you can see, there is a cover skin which is made out of a metal sheet, and then if you look into the cross section, you will see this thick longitudinal member. These longitudinal members are running through the entire length of the wing. So, these thicker ones are called the spars. The thicker ones are called the spars. Longitudinal beam parallel to the wing whose depth equal to almost the wing thickness, attached to both upper and lower skin. So, these are the spars. These are the spars. So, their depth is almost equal to the thickness of the wing. So, if you see, they are spanning from the top skin to the bottom skin. So, sometimes these spars are connected to the top skin and sometimes the spars are connected to the bottom skin. Now, of this spar, the top and bottom flanges of the spar, this one, where it is connected to the skin, are called the spar caps. You can see here the spar caps. And spar webs are the vertical thin member of the spar. So, this portion, this vertical portion is called the spar web. Apart from the spar, there is another longitudinal member that is commonly seen in a semi-monocoque wing is the stringer. Stringers are again longitudinal skin stiffener which runs parallel to the wing, similar to the spar, but then they are smaller than the spar. Their depth is not equal to the thickness of the wing. They are smaller, as you can see. These are the stringers. These are much smaller in dimension. So, they are either attached to the top skin and the bottom skin, and the next thing, so these are the two main longitudinal members. So, longitudinal members are there for longitudinal members are therefore two types in wings. One is spar, which is thicker, a larger member, and one is stringer. So, apart from the spar and stringer, there are some transverse members also, which are perpendicular to the length of the beam. So, a transverse member is this portion, if you can see it, which is running along the cross section of the wing. So, these are transverse members and which are called ribs usually. They cover the entire structural cross section of the wing. So, not only in the wing, such kind of structure can be, such kind of design can be seen in tails of an aircraft, as I said before, or any other aerodynamic surfaces, maybe a flap or a larger flap will also have this kind of structure. So, next let us move into fuselage and see what are the component of the semi-monocoque fuselage construction. So, in fuselage construction there are longitudinal and transverse member, but the longitudinal and transverse members are not called ribs and spar as they are called in the wing, tails and smaller aerodynamic structure. In fuselage, the transverse skin stiffeners are called frame or rings. They are the transverse member. They are the counterpart of the ribs that you see in the wings and tails. And another transverse member is the bulkhead, which are much larger component and a heavy frame which is usually seen, which cover the greater portion of the cross section of the fuselage, and they are usually seen at the front of the fuselage and at the back of the fuselage. They are also transverse member, but they are much heavier and larger than the frame of or the ring. So, this too makes the transverse member of a semi-monocoque fuselage. Now, let us come into the longitudinal member. For as I said, for a wing, the longitudinal members were spars and stringer. Here, the longitudinal members are called longerer, which are much heavier longitudinal stiffener, which runs parallel to the fuselage. And apart from longerons, there are stringer, which are smaller skin stiffener, as you have seen in case of a wing. They are smaller longitudinal stiffeners which are parallel to the fuselage and but are much smaller than the longeron. So, these two are the longitudinal stiffener or longitudinal member of a semi-monocoque fuselage. So, now therefore, we can say that for a semi-monocoque structure, the major component is the skin, which is the outermost cover, which gives you the aerodynamic surface and controls the improves the aerodynamic efficiency and controls the drag. That is the skin, the thin skin like structure on the top of the aircraft, covering all the internal structure. The second part is the longitudinal members. and the third are the transverse members. So, as I said earlier, longitudinal member could be spar, stringer, longeron, transverse member could be rib, bulkhead, rings, formers, etc. Now, let us quickly see what are the main structural job of each of these component of the semi-monocoque structure. So, let us start with skin. The main function of the main structural function, the main structural job that the skin does is that it transmits the aerodynamic force that comes on the aircraft to longitudinal and transverse supporting member. That is the primary job of the skin. The second job is to develop